Hello everyone and welcome back. So in the previous lecture we have discussed in details about walk, trail, path, circuit and cycle in graph theory. We have also gone through the concepts of maximal and maximum paths in graph, and towards the end of the previous lecture I have posted one problem for you to solve. So let's go through the solution of that particular problem first. So you were given this graph G in which you were asked to list down all the maximal and maximum paths. In addition to that, you were asked to find the length of the longest path in the graph G. So here I present to you the entire list of maximal paths that we can find in this graph G. You can check on your own that every sequence of vertices presented in this slide is a maximal path of the graph. Out of this entire list of maximal paths, the last four, which are of the maximum length, will constitute the maximum paths in the graph. And once you obtain the maximum paths, its length will be the length of the longest path in the graph. Accordingly, the length of the longest path in the graph G is 7. Moving forward, in today's lecture we are going to cover these few topics, and the main objective of this lecture would be to cover the concept of subgraph of a graph, and in relation to that we will be learning some particular types of subgraphs as well. So without any further delay, let's start today's lecture, and the topic of discussion is subgraph of a graph. Now, before we proceed to the concept of subgraph, we must have a very clear idea about subset and proper subset in a set theory. So let's have a very brief discussion on the same. Suppose A is any set of elements as given here. Now a set B will be called a subset of A and will be denoted in this form if every element of B is also an element of A. For example, suppose I take a set of elements 5, 8 and 12. Now here every element of this set capital X is also an element of the set A. 5, 8, 12, each of them belongs to A. That indicates by the definition of subset that X is a subset of A. Now if I consider a set Y containing the elements 2, 7, 8, 9, 10. Now here you can see, although 2, 7, 8 and 10 are the elements of A, 9 which is present in the set Y is not an element of A, and that indicates that Y is not a subset of A. Now what about if I take the set of elements as 2, 5, 7, 8, 10, 12. See, the elements of the set Z are all the elements of the set A. So it satisfies the criteria as given by the definition of subset. Any element of Z is also an element of A, and hence Z is definitely a subset of A. What if I consider a set which is the empty set phi, does not contain any element, it is the null set. Now by default, since it does not contain any element, it has to be the subset of any set. So it has to be the subset of A. So we have to remember some particular points, that a set itself is always its subset, and the empty set phi is always a subset of every set. Now in relation to this, let's have a discussion on proper subset. So a set B will be called a proper subset of A and will be denoted like this if every element of B will be an element of A, and along with this there must exist an element in A such that it does not belong to B. That means if I wish to say that a set B is a proper subset of a set A, then first of all it has to be a subset of A, and another important criteria has to be satisfied, that is, there must exist an element in the set A which does not belong to B. So A must contain an extra element. So satisfying this criteria, we can say every subset of a set is also a proper subset of that set except for the whole set itself. For example, if I take the set X as 5, 8, 12, it is a proper subset of A because not only X is a subset of A, that is every element of X is also an element of A, but also there are extra elements in A which are not in X. So X is a proper subset. If I take the set Y as 2, 7, 8, 9, 10. Now here Y is not even a subset of A because it contains an element which does not belong to A. So it dissatisfies the criteria of being a subset. Now if it is not a subset, then definitely it is not a proper subset also. Now if I take the set Z as 2, 5, 7, 8, 10, 12. So definitely Z is a subset of A, but A does not contain any extra element that Z does not have. So Z does not satisfy, or Z does not qualify to become a proper subset of A. So although Z is a subset of A, Z is not a proper subset of A. And what about the empty set phi? Again, it does not contain any element, and definitely A has so many extra elements that W does not have. So phi definitely is a proper subset of the set A. Now we proceed to the definition of subgraph of a graph. So basically, if we have a graph G, then any graph H will be called a subgraph of the graph G if two conditions are satisfied. First of all, the vertex set of the graph H should be a subset of the vertex set of the graph G, and the edge set of the graph H should be also a subset of the edge set of the graph G. That means for H to be a subgraph, its vertices must be some vertices of the graph and its edges also must be some edges of the graph only. So here goes the definition of subgraph, as you can see on this slide. And when we call H as a subgraph of G, we can also term it in the way that G contains the graph H. In this context, it should be noted that every graph can be considered as a subgraph of itself. So now let's go through some examples to have a clear idea about this concept. So here we have a graph G whose vertex set Vg and edge set Eg are mentioned in this slide. Now here we have a graph H. Let us see if H is a subgraph of G or not. So for that, let us find out the vertex set of H. As we can see here, the vertices that we have are U, V, W, X, Y, Z. So clearly the vertex set of H is a subset of the vertex set of G, because every element in VH is also an element of the set VG. That is, the first condition for being a subgraph is satisfied, but we also need to check that the second condition should be satisfied. So let us find out the edge set of H. Now the edges which are present in the graph H are UY, VW, and we have WZ. Now if we see these edges UY, VW and WZ, they are all present in EG as well. That means EH is a subset of EG. Now this is the second criteria that must be satisfied if H has to be a subgraph. So we see both the conditions are satisfied by the graph H and it qualifies to be a subgraph of the graph G. Therefore, this graph H is a subgraph of G. Now for the same graph G, let's check if this particular graph H is a subgraph. So the vertex set and edge set of G are presented over here. Now let's find out the vertex set and edge set of H. So VH is the set of vertices, that is U, V, W, X and Z. Clearly we can see U, V, W, X, Z are all present in V of G. That means V of H is a subset of V of G. So the first criteria is satisfied. Let us find out the edge set of H. So here we have UX, we have VX and WZ. So we can see although UX and WZ are present in EG, but this edge Vx is not present in the edge set of G. That is, this edge is not present in the original graph G. Hence, E of H, the edge set of the graph H, is not a subset of the edge set of the graph G. That indicates second criteria is not satisfied and therefore we can say that H is not a subgraph of G. Next, let's find out the vertex set of H, that is U, V, W and Y, which is definitely a subset of capital VG. Therefore, the first criteria is satisfied. Let's find out the edges of H. So here in H we have only one edge UV and that is present in the edge set of G. So E of H is a subset of E of G, which makes H a subgraph of G because both the conditions are satisfied. Next we have here the vertex set of H as U, V, W, X, Y, Z. So that is nothing but definitely a subset of VG. Now the edge set of H is phi. It does not contain any edge. The graph H is edgeless graph and we know that phi is a subset of every set. So E of H, that is phi, is definitely a subset of E of G. So both the conditions for being a subgraph are satisfied here. Therefore H qualifies to be a subgraph of G. Next here, V of H is U, V, W, X, Y, Z and E of H is U, V, V, W, W, X, X, U, U, Y, W, Z. Clearly we can see V of H is a subset of V of G because every element here is also an element here, and E of H is a subset of E of G because every element here is also an element here. Both the conditions 1 and 2 are satisfied, therefore H qualifies to be a subgraph of G. Now here we can see clearly here H is nothing but the graph G itself. So we can say that every graph is a subgraph of itself. Let's now check another example. So here we have another graph G with this as the vertex set and EG as the edge set. So here we have a graph H. Let's see if it is a subgraph. So V of H is the set containing the vertices of H, that is A, B, C, D, E, G and H. If you observe carefully, every element in VH is also an element in VG. So VH is a subset of VG. Now we find out the edge set of H. It contains the edges AB, BD, CD and EG. Now if you observe carefully, AB, BD and CD, these elements in AH are also elements in EG, but the edge EG present in H is not an edge in the graph G. That means E of H is not a subset of E of G, and therefore H is not a subgraph of G, because although the first condition is satisfied, the second condition is not satisfied. Now for this graph H, the vertex set is the set containing A, B, C, F, G, H. Definitely we can see V of H is a subset of V of G. Let's check for the edge set of H. So the edges present in H are AB and AC, and we can see that AB, this element is present in EG, but AC, this edge is not present in the graph G. Therefore E of H does not satisfy to be a subset of EG, because EH contains an element which is not there in EG, and therefore H does not satisfy to be a subgraph of G. Now for this graph H, the vertex set is A, B, C, D, E, F, G, H. So V of H is definitely a subset of V of G. First condition is satisfied. Let's check the second condition. So find out the edges. Here you don't have any edges, so it is an empty set phi, which we know is a subset of every set. So EH is a subset of EG, and therefore H satisfies to be the subgraph of G. Now here if you observe carefully, the graph H is nothing but the graph G itself, and we know every graph is a subgraph of itself. So the graph H definitely is a subgraph of G. And if you wish, you can definitely check this by finding out the vertex set and the edge set of H. You will see the vertex set of H is equal to the vertex set of G, and therefore we can say vertex set of H is also a subset of the vertex set of G, and edge set of H will also be equal to the edge set of G, and hence can be called a subset also. Therefore both the conditions are satisfied and H is a subgraph of G. Now let's see for this graph G. Now here we are given a list of graphs, and let's check if any of these are subgraphs. So in the very first example, we have only the vertex Y. Definitely the vertex is a vertex of G also, and it doesn't have any edge. So definitely the edge set of this graph is a subset of the edge set of G. So this qualifies to be a subgraph of G. In the second example, we have the vertices X, Y, V, which are also vertices of the graph G, and the edges X, Y and Y, V are also the edges of G. So this is a subgraph of G. In the next example also, the vertices U, V, X, Y are vertices of the graph G, and the edge U, V is also present in G. So this is also a subgraph of G. Here we have all the vertices U, V, W, X, Y, which are vertices of the graph, and there is no edge. So definitely phi is the edge set of this graph, which is a subset of edge set of G, and it qualifies to be a subgraph. Here also all the vertices and edges are all present in the graph G itself, so this is also a subgraph of G. And lastly, here we have the graph G itself, and we know every graph is subgraph of itself, therefore this is also a subgraph of G. Now we move to the next important concept, that is proper subgraph of a graph. Now here goes the definition of proper subgraph. So we call a subgraph H of a graph G as a proper subgraph when either the vertex set of H is a proper subset of the vertex set of G, or the edge set of H is a proper subset of the edge set of G, or both the conditions are satisfied. Now keep a note on this, that when we call a graph H as a subgraph of a graph G, we need to satisfy two conditions. Both the conditions are to be satisfied, that is, the vertex set of H should be a subset of the vertex set of G, and the edge set of H should be a subset of the edge set of G. Now when we want to call a graph H as a proper subgraph of G, then either the vertex set of H should be a proper subset of the vertex set of G, or the edge set of H should be a proper subset of the edge set of G, or both the conditions must be satisfied simultaneously. That means either the graph G should have an extra vertex that H does not have, or it should have an extra edge that H does not have, or it can have both extra vertex and extra edge that H does not have. So in either condition we can say the subgraph H is a proper subgraph of the graph G. So to be a proper subgraph, first of all, the graph has to be a subgraph. That has to be kept in mind. So let's see some examples. Now before that, let's keep a note on this important point, that no graph is a proper subgraph of itself. Like no set is a proper subset of itself, similarly no graph can be a proper subgraph of itself, because it cannot have any extra vertex or any extra edge that it itself does not have. So let's now see some examples to make this more clear. So here we are given a graph G with VG and EG as the vertex and edge set respectively. So let's see if H is a proper subgraph of G or not. So let's find out the vertex set of H, that is U, V, W, X, Y, Z. So we can see that every element of VH is also an element of VG. So definitely VH is a subset of VG, but there is no extra element in VG which VH does not have. That means V of H is just a subset, but it is not a proper subset of VG. Now we proceed to check for the edge set of H. So edge set of H is the set containing Ux, Vy and Wx. Now we can see each of these elements are present in EG as well, and EG contains some extra elements that EH does not have. That makes E of H a proper subset of E of G. That means the graph G, although does not contain any extra vertex than H, but it contains some extra edges that H does not have, and in that sense we can say that H is a proper subgraph of G. So basically, for a graph H to be a proper subgraph of a graph G, first of all H has to be a subgraph of the graph G, and moreover the graph G should have at least one extra vertex or an extra edge, or both extra vertex and extra edge compared to the graph H. Now let's see for this graph. So here we can see the vertex set of H is U, V, W, X, Z. So definitely vertex set of H is a subset of vertex set of G, and VG contains an extra element that VH does not have. That makes VH a proper subset of VG. Now let's check for the edge set. So edge set of H contains Ux, Uz, Wx, Wz. So clearly every element of EH is also an element of EG, and there is an extra element Vy in EG which is not in EH. So that means E of H satisfies to be a proper subset of E of G. Therefore, the graph H is a subgraph of G. In addition to that, graph G contains an extra vertex as well as it contains an extra edge also, enough for me to conclude that H is a proper subgraph of G. So here we see the vertex set of H is a set containing U, V, W, X, Y, Z, that is all the vertices of G only. So VH is a subset of VG, but it is not a proper subset of VG. Let's see for EH. EH is phi, as there is no edge here, which is definitely a proper subset of E of G, because EG contains extra elements that EH does not have. Therefore, the graph H is a subgraph of G, as well as it is proper subgraph of G, because the graph contains some extra edges that the graph H does not have. So here the vertex set of H contains all the vertices of the graph G, so it is equal to the vertex set of G itself, and if they are equal, definitely V of H is not a proper subset of V of G. Similarly, E of H also is equal to E of G, because this graph H contains all the edges of the graph G. So clearly E of H is also not a proper subset of E of G. Although H is a subgraph of the graph G, here H is not a proper subgraph of the graph G, because G does not contain any extra vertex or any extra edge that H does not have. Therefore, H is just a subgraph, but it is not a proper subgraph of G. Let's check for another example. This is our graph G. Here if you observe, you will find the vertices of the graph H are vertices of the graph G, and the edges of the graph H also are edges of the graph G only. That makes H a subgraph of G. Now, in order to deal with the concept of proper subgraph, we can see that G contains some extra edges that H does not have. G also contains an extra vertex that H does not have. That makes H a proper subgraph of G as well. Here the vertex set of H is definitely a subset of the vertex set of G, and the edges in H are also edges of the graph G only. That means H is a subgraph of G, and we can see the graph G contains some extra edges that H does not have. Although it doesn't contain any extra vertex, but some edges are extra, and that's enough for me to conclude that H is a proper subgraph of G. Here the vertex set of H is the same as the vertex set of G, so definitely H contains vertices of the graph G only. Now coming to the edges, we can see there are some edges in H like X, Z and Y, V, which are not there in the graph itself. Now it is not possible for any subgraph to contain edges which are not in the graph. Therefore H is not a subgraph of G, because the edge set of H is not a subset of the edge set of G, and that is enough for me to conclude that H is not a proper subgraph also, because first of all it has to qualify as a subgraph, then only we can proceed to check if it is a proper subgraph or not. Next, here we can see the graph H is same as the graph G, so definitely H is a subgraph of the graph G, but H is not a proper subgraph because G does not contain any extra vertex or any extra edge that H does not have. So H is not a proper subgraph of G. Let's check for this particular graph G. Now in the first example, it is not only a subgraph of G, but it is a proper subgraph of G also. In the second example, this graph is also a subgraph of G, and G contains extra vertices as well as extra edges than this graph, therefore it is a proper subgraph also. Now the third example also, it is not only a subgraph, but it is a proper subgraph of G. The fourth example also is a subgraph as well as proper subgraph of G. In the fifth example, we again have vertices and edges of the graph only, so it is a subgraph, and the graph G contains some extra edges and vertex, therefore it is a proper subgraph. In the last example, we can see it is the entire graph G itself, so although it is a subgraph of G, it does not qualify to be a proper subgraph. Next, we move to another vital concept, that is spanning subgraph of a graph. So we define spanning subgraph of a graph as a subgraph which contains all the vertices of the graph. That is, the graph H will be called a spanning subgraph of the graph G if H is a subgraph of the graph G and the vertex set of H is equal to the vertex set of G. So here goes the definition of spanning subgraph. You can go through this slide. And again, an important note, every graph can be considered as a spanning subgraph of itself. Now let's see some examples. So given a graph G, let's check if H is a spanning subgraph of G or not. So here, as we can clearly observe, that H contains vertices of the graph itself and there is no edge in H, so definitely H is a subgraph of G. Now whether it is spanning subgraph or not, so we can see the vertex set of H is the set containing U, V, W, X, Y, which is same as the vertex set of G. So VH is equal to VG, and that is the criteria that should be satisfied to be a spanning subgraph. So H is a spanning subgraph of G. Next, here we have a graph H, and here we can see H is definitely a subgraph of G because the vertices of H are vertices of G only. The edges of H are also edges in G. Therefore, H is a subgraph of G. But whether it is spanning subgraph or not, answer is no, because H does not contain the vertex Y that G has, because V of H is equal to U, V, W, X, and this, although is a subset of VG, it is not equal to VG, and therefore H is not a spanning subgraph of G. Here we can see H is definitely a subgraph of G, and it is also a spanning subgraph of G because V of H is equal to V of G. All the vertices of the graph are present in H. Therefore, H is a spanning subgraph of G. Now here, if we observe clearly, we will see that H is not even a subgraph of G, and the reason is H contains an edge which G does not have. Okay, so H is not a subgraph of G. Now if H is not a subgraph of G, then definitely does not qualify to be a spanning subgraph also. Here if we see the graph H is nothing but the graph G itself. We know every graph is a subgraph of itself, and we also know that every graph is a spanning subgraph of itself. Here H is a subgraph of G because the vertices and the edges in H are also the vertices and edges of G only. That makes it a subgraph. And since the vertex set of H is equal to the vertex set of G, that makes it a spanning subgraph. So we can remember it in this way, that every graph is a spanning subgraph of itself. Let's see another example. So here we have a different graph G, and here as we can see in the graph H, the vertices and the edges in H are vertices and edges of G only. So H is a subgraph of G. And if we see closely, we will find that the vertex set of H is equal to the vertex set of G. H contains all the vertices of the graph G. So it is not only a subgraph, but it is also a spanning subgraph of G. Here H contains vertices and edges of the graph G only, that makes H a subgraph. But we can see that the vertex set of H is not equal to the vertex set of G because G contains a vertex X that H does not have. So although H is a subgraph of G, H is not a spanning subgraph of G. Next, here we see that the vertex set of H is the same as the vertex set of G, but H is not even a subgraph. Why? Because H contains some edges like uy and vx which are not present in the graph itself. So H is not a subgraph and therefore H is not a spanning subgraph also. Here we can see H is the same as the graph G, and we know every graph is a spanning subgraph of itself, so H is a spanning subgraph of G. Now let's check for this graph G. Now here we can see the first graph containing the only isolated vertex y obviously is a subgraph of G, but it does not contain all the vertices of the graph and hence it is not a spanning subgraph of G. Similarly, the second graph is also a subgraph of G but not a spanning subgraph of G because the vertex set of this graph is not equal to the vertex set of G. For the third graph also, although it is a subgraph of G, it is not a spanning subgraph because the vertex W is not present here. Now the fourth graph is definitely a subgraph of the graph and also the vertex set of the graph is equal to the vertex set of the graph G. That makes it a spanning subgraph of G. Next, this graph is also a subgraph of G, but it is not a spanning subgraph because the vertex Y is not present here. And lastly, this graph is the graph G itself, and we know every graph is a spanning subgraph of itself, so this is a spanning subgraph. Next, we move to another very important concept, that is induced subgraph of a graph. Now, the definition of induced subgraph goes like this, that a subgraph H of a graph G is defined as an induced subgraph if whenever two vertices uv are in H such that the edge uv is present in G, that is u and v are adjacent in G, then u and v must also be adjacent in H. Let's see with the help of an example so the definition becomes more clear to us. So here we have a graph G as presented in this slide, and on the right hand side we have a graph H. So we can see that the graph H contains the vertices and edges which are present in the graph G only. That makes H a subgraph of G. Now the graph G contains extra vertices as well as extra edges that H does not have, and that makes H a proper subgraph of G. Now H does not contain all the vertices of the graph G, that is vertex set of H is not equal to the vertex set of G, and that is why H is not a spanning subgraph of G. Now let's check if H is an induced subgraph or not. So the vertices that are present in H are A, B, C and F. So let us write down the vertex set of H. Now we can see that the vertices A and F are present in the vertex set of H, and in the graph G, AF is an edge, that is AF are adjacent in the graph G, but AF is not an edge in H, that is A and F are not adjacent in H, therefore does not satisfy the criteria to be an induced subgraph. So for a subgraph H to be an induced subgraph, we must have this criteria satisfied, that for every two vertices that are present in H which are adjacent in G must be adjacent in H also. So here we can see of these vertices A, B, C, F, A and B are adjacent in G, they are also adjacent in H. B and C are adjacent in G, they are also adjacent in H. C and F are adjacent in G, they are also adjacent in H, but A and F, although are adjacent in G, they are non-adjacent in H. That is the reason H is not an induced subgraph of G. Let's check some other examples. So here we can see the graph H is a subgraph of G. It is a proper subgraph of G. It is not a spanning subgraph of G. Now what about being induced? So we can see the vertices that are present in the graph H are A, B, C, F, and all the adjacencies that are present in the graph G among these vertices A, B, C, F are also present in the graph H. That is, if we deal with the vertex set of H, that is A, B, C, F. Now any two vertices in this set which are adjacent in G are also adjacent in H. Therefore, H qualifies to be an induced subgraph. Let's see for this example. Here H is definitely a subgraph of G. H is a proper subgraph of G. H is not a spanning subgraph of G because the vertices B and F are not present in H. Now the vertices that are present in H are A, C, D and E. So let us write the vertex set of H, that is A, C, D, E, and any two vertices among these which are adjacent in G are also adjacent in H. See, of these vertices, C and D are adjacent, D and E, and C and E are adjacent in graph G, and these are also the edges in H. So H qualifies to be an induced subgraph. Here H definitely is a subgraph of G. It's a proper subgraph of G. It is not a spanning subgraph of G. And if we see the vertices, BH here is equal to B, C, E and F. Now any two vertices from this set, if are adjacent in G, are also made adjacent in H. See, these are the adjacencies among these four vertices in the graph G, and they are maintained in the graph H also. That makes H an induced subgraph of G. Now if we see this graph, here H is a subgraph of G. It is a proper subgraph. It is not a spanning subgraph of G because the vertex A is not present in H. Now see, the vertex set of the graph H contains B, C, D, E and F. Now here in this set of vertices, C and D are two vertices which are adjacent in the graph G. The edge CD belongs to G, but the edge CD does not belong to the graph H. Therefore, these two vertices are such that they are adjacent in the graph G. They are present in this graph H but are not adjacent. Therefore, it satisfies the criteria for being induced subgraph. Therefore, this graph H is not an induced subgraph of G. Now, in relation to this, we come to two very important concepts. One is vertex induced subgraph and other is edge induced subgraph. So, let's go through the definition of vertex induced subgraph first. So, we are dealing with a graph G and T is a non-empty set of vertices of the graph. Then the subgraph of G, which is induced by this set of vertices T, will be called the vertex induced subgraph, and it is denoted by this expression. So what does it mean basically? So we have a graph G having some vertices and we take T as a non-empty set of vertices of the graph itself. So T contains some vertices of the graph. Now what will be the vertex induced subgraph of G induced by this set of vertices T? It will be the subgraph which will be created by only these vertices that T contains, and it will contain all the adjacencies among these vertices which the graph has. Let's see some example. So here we have this graph G whose vertex set contains all these elements U, V, W, X, Y and Z, and we choose a set of vertices T as U, W, Z and Y. So what will be the vertex induced subgraph of G induced by this set T? This graph will be the subgraph of G which will be created by these vertices. So we will need U, we will need W, we will need Z and we will need Y. These vertices will be present and whatever adjacencies exist among any two of these vertices in the graph will be present in this induced subgraph. So we can see in the graph among these four vertices UW are adjacent, WZ are adjacent, UY are adjacent, ZY are adjacent and UZ are adjacent. So these are all possible adjacencies among any two vertices of this set T. So this is the vertex induced subgraph induced by this set of vertices. If I change my set of vertices, if I change my set T, I will have a new set of vertices of the graph. I will take only those vertices in my subgraph and I will draw all the adjacencies that exist, all the edges that exist between any two vertices of this set only in the original graph. So let's take some other set of vertices. So T here is VWXY. So the vertex induced subgraph of G induced by this set T will be the subgraph which will be created by the vertices V, W, X and Y. So these will be the only vertices present in your vertex induced subgraph. And what about the edges? Only those edges which exist between any two of these vertices. So in the graph we have edge between VW, WX and XY. See, any other edge in the graph will bring up a new vertex in this subgraph and we cannot enter any new vertex. When we are given this set of vertices, our vertex induced subgraph must only show these vertices and all those edges will be shown which exist between any two vertices of this set. So this is our vertex induced subgraph induced by this set T. Again, if I change my set T to UZ, then my vertex induced subgraph induced by this set of vertices T as UZ would be the subgraph that is created by the vertex U and the vertex Z and any adjacency if there exists in the graph between these two vertices. Now we see in the graph U and Z are adjacent, so I will make them adjacent in this vertex induced subgraph. So this is G of T. Now let's check for this graph G. Now in the first example, we have drawn here the vertex induced subgraph induced by the set of vertices UVW. So see, only UVW are drawn and all the adjacencies that there are among these vertices in the graph, we have drawn all of them. So this is the vertex induced subgraph induced by this set of vertices. Now if instead I take this set of vertices, then I will draw the vertex induced subgraph considering only those vertices VWX, and I will draw all the edges which exist among these vertices in the graph. So there are only two edges that exist between any two vertices of this set in the graph, and I draw both of them. Since X and V are non-adjacent in the graph, so there is non-adjacency in the subgraph also. Now again I change my set of vertices to UVX, so I take only those vertices UVX, and since among these vertices only there is adjacency between U and V in the graph, so I draw that edge only. So this is how we create vertex induced subgraph. Given a set of vertices, we take only those vertices in the subgraph and we draw all the adjacencies among them that are present in the graph itself. That makes our vertex induced subgraph. In a similar manner, we can define edge induced subgraph also. Let's see with the help of an example. So here we have a graph G and X is the set of edges BC, AF and C. Let me mark those edges in the graph BC, AF and CE. So if I need to draw the edge induced subgraph of G induced by this set of edges, then I will have to draw the subgraph that will contain only these edges. So I will have BC, I will have AF and I will have CE. Okay, so this is the edge induced subgraph induced by this set of edges. So we will draw only those edges and automatically the end vertices of those edges will come into the picture. So this is the edge induced subgraph. If I change my set of edges to AB, CD, so I need the edges AB and CD in my induced subgraph. So the edge induced subgraph induced by this set of edges would be the subgraph containing only these edges, that is AB and CD. If this is the set of edges, then the edge induced subgraph of G induced by the set of edges X would be the subgraph containing these edges. So we will have AB, we will have AF, we will have CD, and definitely we will have CE. Now here we have so many edges, so we have named them as E1, E2, E3 up to E12. So let's see what will be the edge induced subgraph induced by the set of edges E4, E6, E8 and E10. So I need E4, I need E6, E8 and E10. So I will draw the edge induced subgraph as the subgraph containing only these edges. So this is my E6, then I have my E8, this is E10 and this is E4. So these are U, X, Y, W, V. Automatically the end vertices of those edges will come into my picture. So this is the edge induced subgraph induced by these edges. Again, for the same graph, if I want to draw the edge induced subgraph induced by this different set of edges, then I will only draw those edges. This is my E1 and vertices are UV. Then I have E2 and vertices are VZ. Then I have E3. So I get the end vertex Y also. I have E11. So this was E2, this was E3, this is E11. So I get the vertex W into my picture. And I have E12, that is this edge, and X comes into the picture. So these are the edges that I will have and automatically the vertices will come. For E7 and E10, I will have the edge induced subgraph looking like this. This is E7, that is between W and X, and E10 is between X and U. Done. So for this graph G, we can see the edge induced subgraph induced by E2, E3, E6 will contain only these three edges. The edge induced subgraph induced by E1 and E7 will contain only the two edges E1, E7, and here E1, E4 and E5 only will be present in the edge induced subgraph. So that's all for today. I really hope that you had a clear idea about subgraph from today's lecture. So if it was of any help, then please do like, share and subscribe to our channel. We really welcome your queries and suggestions. So if you do have any, please write in the comment section below. I am going to meet you again in the next lecture with some new topic. Till then, thanks for watching. Take care and bye-bye.